All right, let's talk about some fossils. Again, we're going to be continuing with chapter 25. As we can see, we have an example of a fossil, which I obtained from one of the government websites. There are a ton other fossils there. You can go ahead and link to that if you choose to take a look and read about some of them. Continue with what's really in chapter 20. Overall, fossils have given us a ton of information throughout the years, and it allows us to see the changes in organisms that have happened over the course of time. So if you take a look at this right here, we've got all different types of organisms, and you can see the changes in the structures and what they look like over the course. It takes a long time. Here we're talking about millions of years and differences within hundreds of thousands. So now it's important to remember that not all organisms can fossilize. In fact, very few of them have fossilized, and even less than that have been discovered. So we know that there's a lot more fossils that exist that we just haven't discovered yet, and we know that there are so many much more organisms that had existed in the past that we will never find any evidence of because they do not fossilize. Now, the fossil record is biased, right? So this is what I'm explaining. It's biased in favor of the species that can fossilize, first of all, right? So for those that can fossilize, they need to have hard parts, okay? And they should have shells or skeletons. Now, another couple biases in terms of the fossil record include the following, right? So, if they were abundant and widespread, meaning they were found in a very wide range of area, and there were enough of them for us to be able to find. If you think about it, if there was a particular species that existed for maybe a short period of time in only one geographic area, which hasn't been studied yet, then we haven't found it yet, right? So we do not, the fossil record that has been already discovered is biased towards those things that it probably were quite abundant, right? So they weren't that rare. And then they have to have existed for quite a bit of time, right? So the longer an organism or a species existed, the more you're going to see in the fossil record. Okay, so does that make sense? Again, the fossil record is very important. It can tell us a number of things. However, it is limited in the fact based on these three criteria. Now, there is sedimentary rock. Over time, these rocks are deposited, forming layers, and the layers are called strata. This is basically where most all the fossils are going to be found. Okay, so this is a very, very good source of fossils, these sedimentary rocks, or the strata. Look at how fossils are dated. So the fossil record tells us information, first of all, about structures. We can see the organism, and we can date them, right? So there are a couple different ways of dating fossils. So ways is called relative dating. Relative dating is basically inferring the age of a particular fossil based on its position relative to other fossils. For instance, if we take a look at this set of strata right here, so these are examples, you can see the fossils inside each of the strata, right? So the deeper ones, the ones that are not close to the surface, are going to be older, okay? So this is an older stratum which existed much, much more longer ago than the ones above it. And then, of course, the most recent ones are going to be on the surface or closer to the surface of Earth. So this would be more like present day up here. So if we knew the age of this fossil here, but we wanted to date this fossil here, then we could say that this fossil here is older than this fossil. So we can estimate the age in which that fossil is based on where it is in the strata relative to fossils in which we know the age of. Okay, so that's relative dating. It's basically in relationship or relative to the other fossils that are in the strata around it. Absolute dating is basically gives you a number. So this can give you a number, really a range. It's not exact, and the further away you get in terms of age, the less exact or the larger that range becomes. Radioactive dating is done by the use of isotopes. So if you remember what an isotope is from General Biology 1, remember isotopes are a particular element, but a different form of a particular element, and that form has a different number of neutrons. And of course, the ones that release energy, so these are the radioactive isotopes that are used. So remember, the radioactive ones start decay and they release this energy over time as they're decaying. Well, each isotope has what's called a half-life. The half-life is the amount of time, right? So usually in years, that's required for half of the original isotope, right? So the parent isotope to decay by 1/2 of that amount. Right, so if we look at the curve here, we see the fraction of the parent isotope. We can say, let's just assume this is 100% up here. So whatever that amount is, it's 100%. Okay. The time it takes to get to 50% is the half-life of that particular isotope. Now for carbon, that time is 5,730 years. So after 5,730 years, when you measure, let's say we measure the carbon-14 initially, the difference, right, between that and once the organism or that carbon-14 became reduced by 1/2 that amount of time would have passed by. And then 1/2 again, right? So it would take another 5,730 years for that 50% to be reduced or decayed down to 25%. And then 12.5%, and so on and so forth. Curve again. I'm going to show you the relative to percentages, right? So we've got, we'll start out at 100%. And then it takes 5,730 years to go down to 50%, and then another 5,700. So each of those are counted as one half-life. Okay, so after 4 half-lives, 1/16 of that substance should exist. Now, it's important to remember that, or to know that carbon dating can only be used up to, for fossils, or accurately dating or somewhat accurately dating fossils up to about 75,000 years. And I think in your lab manual it says about 100,000 years. So between 75 and 100,000 years, it can be used to date fossils. Now, going back to this percentage, if we put it in terms of the amount of the substance that existed, so to make it simple, I made it 100. So let's say at 100%, there was 100 milligrams of that substance. Again, it would take 5,730 years to reduce down to 50 milligrams if we're using carbon as the isotope. Same thing, 25 milligrams, 12.5 milligrams, 6.25, so on and so forth. Example of a problem. Okay, so here, I wouldn't worry too much about, sometimes the wording can get a little bit confusing. So here it says carbon-14 is commonly used isotope for radiometric dating. It decays to nitrogen-14 with a half-life of 5,700 years. Remember, we talked about it was about 5,740 years, but it's evened out at this point. So we're going to use the easier number to use to calculate. So here it says a biological sample is found to have 1/16 as much carbon-14 as there is in the atmosphere. So it's all relative to, let's say, the carbon-14 is atmospheric carbon-14, which that's like present day, so that we can say that that's 100%. But we have this biological sample that it was, let's say it was a fossil that died long ago. Okay, so long ago it was at 100%, but now it's at 1/16 of that 100%. So what is 1/16 of 100%? How many half-lives is that equal to? So first you want to find out, so we want to determine how old this sample is, but first you want to find out how many half-lives have passed, right? So that's like doing this, right? So we have 1/2, okay? How many times do you multiply 1/2 by itself to get to 1/16? Okay, so that's like doing this times 1/2 times 1/2 times 1/2, right? So we've got 2 times 2 times 2 times 2. That's 2 times 2 is 4, times 2 is 8, times 2 is 16. So that is 1/16 right there. So look, we've got 4 half-lives have passed. Okay, so we know n equals 4. Okay, so we're trying to find n. How many times, how many half-lives have passed over that course of time? We found that. Okay, so n equals 4. Now, that's just how many half-lives. So that's not how old the sample is. We know that each half-life takes 5,700 years in this case. So now we need to take 5,700 times 4. Right? So we've got 5,700 times 4. And that's going to be the age of your sample. You had some time to calculate that. That's not working. 22,800 years. So let's say this is an example of a problem. This would be your answer right here. Okay, so there's a couple sample problems in your lab manual, which you'll get some practice calculating. So again, it's important to remember that fossils have provided a ton of clues about structures and changes in organisms over time, but it's important to remember that fossil data is limited, okay, because it's biased to those organisms that have lived for a long time, those organisms that were widespread and quite diverse in geographic area, and those organisms that can fossilize. All right, so this is just a little something that I'm suggesting you kind of do on your own, right? So this isn't something that you need to turn in. What I would do is maybe create some sort of timeline representing all of geologic time. I'm not going to talk about geologic time. That gets kind of monotonous and boring. Just it's really interesting that all these different time periods and basically it's from more broad to more specific. We've got eons, we've got eras, periods, epochs. And in your lab manual and in your textbook, it describes those and what types of organisms arose during those times. And it'd be kind of interesting for you to create your own timeline. You could make a timeline. You could make a concept map. You could make a flow chart showing the relationships between those, and then what types of organisms arose during those times. And then it'd be nice to kind of look at, remind yourself of endosymbiotic theory and look up what serial endosymbiosis is. We're going to kind of talk about that when we get to protists. And then kind of remember, this is something that you had to discuss in General Biology 1, right? So what evidence, right? What evidence, structural and components within these organelles support the endosymbiotic origin of the mitochondrion and the chloroplast? All right, so those are just some a suggested activity and some questions to ponder while you are during your study.